Hello everyone, and welcome to lecture 4 of EEE 3308C Electronic Circuits 1. I hope all of you are staying safe in this storm. And for today's lecture, what I thought is that I'll just go ahead and record the lecture so that you can see it at your own time. Now, during Monday's class, we had started discussing about amplifiers, and we talked about the gain of the amplifier in the form that the gain is basically the AC output voltage divided by the AC input voltage for the amplifier. So if we sort of write that down in terms of the equations, so the overall voltage gain in this case, let's write that as AV. So this is amplifier, which is a voltage amplifier, and that voltage gain is written as del V out, which is an AC quantity at the output, over del V in. And why we are talking about the del or the small increment in the output and input voltages? Because that's what mathematically the AC quantities are, that they are small changes at the output and the input. So that's why del V out over del V in, or effectively dV out, dV in, that's the derivative of your output voltage with respect to your input voltage, that becomes your gain. Now, if you think about the voltage transfer characteristics or VTC, that's basically your plot of V out versus V in, which is shown here. That V out over V in plot looks something like this. And we'll see this in a while, why it looks like this. But for now, what we can infer from this particular plot is that the gain of this plot gives you the gain. But then again, the gain or the slope of this plot at very low V in is 0, which is here. The slope of this plot at very high V in is also 0. Now, this is the value of the V in, the DC value around which you will be putting your small AC signal. So if that DC value is very small or very large, then you don't expect a lot of gain out of the amplifier. And that's what we call biasing, that at the input of the amplifier, it will be a VDC combined with a small AC input. So you have a DC term and an AC term that creates your overall input of the amplifier. This DC term creates the bias, which effectively means that in the voltage transfer characteristic, you want to be somewhere in the middle. You do not want to be, you do not want to have a very small value or a very large value for the DC term. You want to be here at almost half of the VDD point. And at that point, if you provide a small amount of input voltage, input AC voltage, that you can expect to be amplified at your output. And that's what we are showing here in terms of the graphical representation. That let's just assume that your DC point or the biasing point or the quiescent point. So it's also called a Q point or a quiescent point, which means that this is the fixed point of the amplifier. So just go through this handout to understand more about the quiescent point or the Q point or the biasing point. But what it really means is that you first need to select your DC point to be somewhere where you can expect gain out of the amplifier. Now, if you have a small input swing, because your gain is something that is larger than 1, or the derivative of this plot with respect to V in is larger than 1, your output will be higher than 1. Now, of course, as you see that as your V in is increasing, your V out is decreasing. What that means is that in this plot as well, if you just plot it graphically, and if you follow these dotted lines, you'll see that when you have a positive cycle of the sine wave at the input side, you have a negative cycle of the sine wave at the output side. Similarly, when you have the negative cycle of the input, you have the positive cycle at the output. That effectively means that the AC gain of this amplifier is a negative quantity. So someone asked in the class, I think 2 classes back, that what does it mean to have the gain as negative, let's say -10? That just means that the magnitude of the gain is 10, but along with that, you have a phase inversion. So whatever was in the positive cycle at the input side becomes the negative cycle at the output side for the sine wave. So that is represented with this negative sign. It does not mean the value of the voltage becomes, if your input is 1 millivolt, it does not become minus 10 millivolt. There's no specific meaning of a minus 10 millivolt in this case. If you are interested in voltages within, let's say, a positive voltage VDD and a zero voltage, which is your ground. So there's no such meaning of a minus 10 millivolt voltage in terms of your input or output. What that negative or what that minus term means is that you have a phase inversion, that your positive cycle at the input becomes your negative cycle at the output, and vice versa. All right, and now this is something we have already looked into, that, okay, if you represent your amplifier as a voltage controlled voltage source or a dependent voltage source, which is given by this AV0 times V in this voltage source. And if you are providing an input voltage of Vs, that has a non-ideal Rs associated with it. This series resistance is the non-ideality of the voltage source. And at the same time, your amplifier also has a non-ideality at its input, that it does not have a infinite impedance, infinite input impedance. Instead, it has a finite input impedance of Rin. Similarly, it has a finite output impedance of Ro. And then at the output side, you have connected a load resistance RL. Now, because of this configuration, you'll see a voltage division at the input side. Then you multiply that with the intrinsic voltage gain of the amplifier. And then again, you have a voltage division at the output side. So these are the three terms that you'll have to consider when you are looking at the overall gain in an amplifier. Now, of course, if the amplifier's input impedance becomes infinite, this first term becomes almost equal to 1, because in the numerator, you have an infinite term. In the denominator, you have infinite plus a small finite term. So, of course, this will become equal to 1. The first ratio will be equal to 1 if your Rin is infinite. Similarly, if your Ro is 0, or the output resistance of the amplifier is equal to 0, then the second voltage division, that becomes equal to 1. Now, that's why we say that for an ideal amplifier, your input resistance has to be infinite and your output resistance has to be equal to 0. Because in that case, you will not see the effect of these two voltage divisions, or the ratio, the voltage division ratios for both will be exactly equal to 1, which means you will have no voltage division. So in an ideal case, when we look at op-amps later in today's lecture, we'll say that ideal op-amp will have an infinite output resistance and a zero or an infinite input resistance and a zero output resistance. Now, in many cases, you'll see that the voltage gain is expressed in terms of dB scale or decibel scale. Now, if you are familiar with logarithms, this is something you are already acquainted with, that how to represent a voltage term or a current term in terms of dB or decibel scale. The decibel is actually defined in terms of power, that the power gain is represented in dB as 10 times logarithm to the base 10 of P out over P in. So the output power divided by input power, that ratio, when you take a logarithm of that, that is the unit called bell. Now, decibel is basically the 10 times of what you represent with the bell unit. So that's why you multiply that with 10 and you get this 10 log 10 of P out over P in. That's your ideal definition of the decibel scale. Now, of course, power you can represent as voltage multiplied with current. Now, from Ohm's law, you know current is voltage divided by resistance. So you can represent power as voltage squared divided by resistance, which is effectively equal to voltage multiplied with current. So this P out becomes V out squared divided by RL, and P in becomes V in squared divided by R in. In the scenario when RL is equal to R in, which you would assume in many cases in electronic circuit design, that you assume your input resistance and output load are matched. And in that case, this RL and Rin will cancel each other, and you'll be left with 10 times log base 10 of V out over V in whole squared. That's what we are writing over here. And that's the definition of voltage gain in dB scale when you talk about voltages. Now, of course, because of the property of logarithm, this can be written as 20 log 10 of V out over V in. This squared term comes on the left-hand side and gets multiplied with the quantity of 10. You can also represent the current gain of a circuit using decibels, and that becomes 10 log 10 of I out squared over I in squared, just like you had V out squared over V in squared here. And that is again something you can write from the equation of power, because remember, power is again voltage multiplied with current, and voltage, due to Ohm's law, you can write it as current multiplied with resistance. So the overall power can be written as current squared multiplied with resistance. And again, if you assume that your RL and Rin are equal, then the current gain in terms of dB scale becomes 20 log 10 of I out over I in, or 10 log 10 of I out squared over I in squared. Now keep in mind that if you cannot assume your RL and Rin to be equal, then you just need to take care of it mathematically. That you have your 20 log 10 of V out over V in term, but along with that, you will have a 10 log 10 of Rin over RL. So you have the overall power gain to be this voltage gain plus 10 log 10 of Rin over RL. Or you can also represent it as the current gain in dB minus 10 log 10 of Rin over RL. That's your overall power gain. All right. Now, let's discuss a little bit about amplifiers again. So, and keep in mind that we are talking about voltage amplifiers. In last class, we talked about 4 different kinds of amplifiers, depending on whether your input is a voltage or current, or your output is a voltage or current. If your input is a voltage, output is a voltage, you get a voltage amplifier. If your input is a current, output is also a current, you have a current amplifier. If your input is voltage, output is current, you have a transconductance amplifier. And if your input is a current, output is a voltage, you have a transimpedance amplifier. Now, this is again the VTC, or the voltage transfer characteristic, that we had looked into. And the bias points are mentioned here. So for example, this is the bias that you have at your output side, and this is the bias that you have at your input side. So your input voltage that you're applying, that will have this much amount of DC voltage plus a small AC voltage on top. And at the output side, it will inherently develop output DC voltage, and your output AC voltage will be on top of that. And the slope of this curve is effectively gain at every point. This biasing point will also be called Q point or quiescent point for our future discussions. And you have already looked into this. The very simple model of this amplifier is just this voltage dependent voltage source, or a voltage controlled voltage source of AV times V in, where V in is the voltage that you supply from your source. But of course, if this amplifier has non-idealities, you can represent that with a input impedance and an output impedance. Remember, impedance, or Z, is basically the frequency dependent form of your resistance. So earlier we were representing in terms of R, R in and R out, but in a more general form, you can talk about Z in or Z out in case your input and output are capacitive or inductive as well. All right, and this is again something that we have already talked about, that even if you have a source resistance of the voltage source, and if you have a finite load resistance, in case you have your Z in to be much larger than Z source, so the input impedance of the amplifier is much larger, and the Z load is much larger than the output impedance of the amplifier, in that case, your voltage gain will be almost equal to the intrinsic voltage gain of the amplifier, because the voltage divisions happening at the input side and the output side will both yield to be equal to almost 1. So just as an example, in this case, we are showing the voltage division of R in between R in and RS. RS is 1 kilo ohm, R in is 9 kilo ohm. So you have a voltage division ratio of 1/10 over there. Again, in this case, you have a R out of 250 ohms and RL of 1 kilo ohm. So definitely you'll have a voltage division of 1 kilo ohm divided by 1K plus 250 ohms. And overall, you get a voltage output of 720 millivolts if your input is equal to 10 millivolts. All right. Now, this table just shows what would be the value in dB scale if you have a specific voltage ratio or a power ratio. You do not need to remember it, but just keep in mind that this is something you should be able to do even with a calculator. That if you have a voltage ratio of 10:1, that means in dB scale you have 20 dB, because 20 times 10, 20 times log base 10 of 10 is equal to 20. So just remember the formula that gain in dB is 20 times log of base 10 of the voltage ratio. So if the voltage ratio is 10, the entire logarithm term becomes equal to 1. So 20 times 1 becomes 20 dB. Similarly, for power ratio, this has to be 100:1, as you see from the power plot as well. So if you have the equation in terms of power is basically 10 times log 10 base of power output over power input. So that's why the 20 dB is basically a power ratio of 100 or 10 square. 0 dB is 1:1 in terms of voltage ratio and power ratio both. Minus 20 dB is a 0.1 voltage ratio or 1/100 power ratio. Something interesting to note is the 6 dB, which is a voltage ratio of 2. So if your voltage is multiplied by 2, then you say that there is a 6 dB voltage gain. In terms of power, if there is a power gain of 4, you say that there is a 6 dB power gain. The 3 dB or the minus 3 dB point is also something that is interesting to note, that in terms of the voltage ratio, it is 1 over square root of 2. That's your minus 3 dB. And in terms of power ratio, it is half. So many a times when you talk about bandwidths of a circuit, you say that the minus 3 dB point or the minus 3 dB bandwidth is the half power point of the circuit. And this is the reason why. That your half power point, the ratio of half in terms of power is basically your minus 3 dB. And if you just draw the bandwidth of a circuit, so let's say you have a band pass filter and you're interested in the bandwidth of it. So let's say if this is 0 dB, you will look at the minus 3 dB point in terms of the amplitude, and you look at the frequency. So in this case, your x-axis is frequency and your y-axis is power. So if you're looking at the minus 3 dB points in terms of power, that gives you two frequencies, let's say F1 and F2. And F2 minus F1 will actually give you the bandwidth of this particular bandpass filter. All right. Now you can have different models of the amplifier. So for example, what can be there inside your amplifier, or the triangle that we had looked into in the previous scenario. So in the previous scenario, we just represented the amplifier with this triangle, right? That we just assume that it can provide a gain of equal to AV if it is a voltage amplifier. Now, what is there inside this op-amp? What is there inside this amplifier? There could be multiple different things, and toward the end of the course, we'll see that what is actually there inside the op-amp. But again, in this case, we can just assume that there could be a very simple implementation of this amplifier, of this triangular black box, and that very simple implementation could be something that will be called a MOSFET. So we'll be discussing MOSFETs in our later lectures in detail. But for now, you can just assume that what this MOSFET does, that it converts the input voltage to an output current. That's the job of a MOSFET. So the MOSFET, or metal oxide semiconductor based field effect transistor, that converts the input voltage to output current. So the job of the MOSFET is to provide a transconductance. So this is a transconductance amplifier where you have an input voltage and an output current. We'll see why the output is a current in our later lectures. Don't worry about that right now, but this is just to keep something in mind. So the MOSFET-based amplifier is basically a transconductance amplifier. It produces an output current when you present an input voltage. So now you see that, okay, you have an input voltage here, and then because of that input voltage, you create an output current. If you take your output voltage at this point, what would be the equation of that output voltage? The equation of the output voltage will be VDD, and then if you assume that the output current is this, then, and let's call this output current as ID. So this is the point called drain. That's why the subscript D. And again, we'll get to that what does this gate, source, and drain means for a MOSFET. So we'll not discuss it right now, but we'll discuss in one of our later lectures. For now, just try to solve this very simple KVL that your output voltage is VDD minus ID times RD, because ID times RD is the voltage drop that happens across this resistance, and VDD minus that voltage drop will give you the voltage at this point, which is your output. Now, when input voltage is very small, your current will also be small, because this is just a transconductance amplifier. If you provide a small voltage input, the output current will be small. If you provide a large voltage input, the output current will be large. So when ID is small or when input is small, your output is almost equal to VDD, because this ID times RD, this term will be very, very small, which means that if your input is small, your output will be large. So let's draw the VTC, voltage transfer characteristics again, that if your input is small, your output will be large. And keep in mind, right now we are just talking about the overall voltage. We are not talking about the AC voltage or the DC voltage here. So what I mean by the input being small is that even the DC point of the input, let's say, is near 0. So in that case, your output voltage is near VDD. That's what is being represented by this KVL equation. Now, when you keep on increasing your V in, your ID will also increase and your V out will drop after some point. And that's why in your VTC, it looks like this, that as you keep on increasing your V in, your output voltage drops. So now you know why your VTC, or the voltage transfer characteristic, looks like what we had shown before. All right, and the model for this particular amplifier, when you have a MOSFET-based amplifier, the model of it looks something like this. The input side, again, looks very similar. You have a Z in, which is ideally very large. On this side, instead of having a voltage-dependent voltage source, now you have a voltage-dependent current source. So you have a transconductance amplifier, which means that if your input is a voltage, VGS, your output will be GM times VGS, when GM is the transconductance. So GM multiplied with VGS creates a current. Or in other words, GM is basically current over voltage. So you're converting a voltage to a current, that's why the name conductance. And remember, conductance is 1 upon resistance. Now, as you know that whenever you'll have a current source, so this is a current source. Whenever you have a current source, there is a non-ideality with that current source, which is an output impedance, which is in parallel with that current source. So now you have this RO, or the output impedance, which is in parallel with this current source. And ideally, for a current source, the RO, or the output impedance, or the output resistance, needs to be very, very large. Just as for a voltage source, the output impedance needs to be very, very small. And that's why they are duals of each other, that the voltage source will have a small series resistance associated with it. A current source will have a large parallel resistance associated with it. What would be the overall gain in this case? Of course, you'll have this voltage division at the input side. Then you'll basically have a multiply that with the GM times RD in parallel with R0. So you see that R0 is over here, which is from this point to the ground. On the other hand, RD is something that is connected between the output node and the VDD. So why are we saying that this RO, for which the other terminal is a ground, and this RD, for which the other terminal is a VDD, why are we saying that they are in parallel? That is because here, whenever you are talking about gain, as I said multiple times earlier, that you only talk about AC gain. This transistor cannot provide you a DC gain. The amplifier cannot provide you a DC gain. So you're always talking about an AC gain. Now, in terms of AC, in terms of alternating voltages or currents, a ground is a zero potential. Similarly, the VDD, even though it's a supply of your circuit, in terms of AC, it is a zero potential because there is no fluctuation in the VDD in an ideal scenario. What is an ideal VDD? Let's say you have a 3.3 volt VDD or a 5 volt VDD and a 0 volt ground. There is no fluctuation in the 0 volt ground. Similarly, there is no fluctuation in the 5 volt VDD, which means in terms of AC, this is a potential which can be regarded as zero AC potential, and this is also a potential that can be regarded as a zero AC potential. Even though the DC values are different, the AC value is same for both and is equal to zero. And that's why this VDD is sometimes called a virtual ground in terms of AC. So whenever you're talking about AC potentials, this point and this point are the same because they are both virtually at AC ground. And that's why they can be considered to be in parallel. So your overall voltage gain becomes this voltage division at the input multiplied with the current that is flowing out over here. And if you did not have any RD, if you did not have this RD, then all the current would have flown into the R0 resistance. So your voltage at the output would have been GM times R0. On the other hand, ideally assume that RO is infinite. In that case, all the current will be flowing through this RD, right? So there would be no current flow through this RO. In that case, this output voltage that will be developed, that will be GM times RD, of course, times VGS. So GM times RD times VGS would have been the output voltage if RO were infinite. But now, because if you have this non-ideality that RO is not infinite, the parallel combination of RO and RD will determine the output voltage. So as you see that you're still having the effect of the non-ideality at the output side, which is given by this RO. If this RO would have been ideal, if this had been infinite, then you just would have had GM times RD as the output side voltage gain. On the input side, of course, you would still have this voltage division. So if your Zin is infinite and if your RO is infinite, then your voltage gain could be approximated as GM times RD. Similarly, you can implement the amplifier with a bipolar junction transistor amplifier or a BJT-based amplifier. And again, for a BJT-based amplifier, you can represent the circuit in a similar way that there is an infinite or fairly large input impedance. And this transistor is also a transconductance, that it converts the base to emitter voltage, which is basically the voltage between this terminal, which is called a base, and this terminal, which is called an emitter. The base to emitter voltage multiplied with the transconductance gives you the output current. So your equations will still be very similar for this particular approximation. All right. So that brings us to the end of the introduction section of our amplifiers. Next, we'll look at something important that is called feedback, and we'll look into amplifiers with feedback. So before we go into amplifiers with feedback, I would like to quickly discuss about some of the concepts of feedback circuits. So what you have here is an example of a feedback system And what feedback means is that if you have an input Vs coming in, and then you have a gain in the feed forward path or an amplifier in the feed forward path, which is A. Again, this is just AC amplification. There is no concept of DC amplification in this course. The output of the amplifier is V0, but some part of that V0 is fed back at the input side and is subtracted from the original incoming input signal. So this is a subtractor. You have a positive terminal here and a negative terminal here, which just means that your input voltage Vi to the amplifier is equal to Vs minus Vf. But Vf is the feedback voltage, which is a portion of the output coming back towards the input side with a gain factor of, or a feedback factor of beta. Okay. So that's what you have in an ideal feedback system. And this is called a negative feedback system, where you are feeding back the signal Vf in a way that you're subtracting it from the original input signal. If both of them had been plus signs, we would have called it a positive feedback. Now, that's not actually the real definition of positive and negative feedbacks in a strict sense. We generally talk about phases, that if your input phase and the feedback phase are in the same direction, and then you are adding those up, then it's a positive feedback. If they are in different directions, then it's a negative feedback. But that is a more strict definition. This definition is much easier for you to comprehend it at this point, that if you see a negative sign over here, most likely it's a negative feedback, because you'll not assume the phase inversion over here in many cases. Now, just like our amplifier were 4 types: voltage input, voltage output, current input, current output, voltage input, current output, and current input, voltage output. The feedback system can also be of 4 types. And that is dependent on what is your output quantity and what is your feedback quantity. So if your output is a voltage and if your feedback quantity is a voltage, that is called a voltage series feedback. So the first term in the nomenclature defines what is the output quantity. So in this case, the output is a voltage quantity. How do you know that the feedback quantity is also a voltage quantity? Because what you are feeding back here can be added in series. And remember that only voltages are something that can be added in series. Okay. So you cannot have, if you want to add 2 current sources, you have to put them in parallel. But if you want to put 2 voltage sources in series, you can add their voltages. So think about how you just stack voltage sources or batteries in series when you are trying to increase the overall voltage. So voltages can be put in series, currents can be put in shunt or in parallel. So voltage series means your output quantity is a voltage and your feedback quantity is fed back in series, which means it has to be a voltage. Similarly, you can have a voltage shunt configuration, which means that your output quantity is a voltage, but your input quantity is something that is fed back in shunt or in parallel, which means that the input quantity has to be a current. And this is what you see in this case as well, that your input was a current and you're feeding back the quantity IF also in current. That's why they are being added at the same node. On the other hand, in this case, you are trying to add them in series by putting voltage sources in series. You can have a current series feedback, which means that output quantity is a current and the feedback quantity is fed back in series, which means that it has to be a voltage. You can have current shunt feedbacks, which means output quantity is a current and the feedback quantity is fed back in shunt, which means it's also a current. Now, if you want to find out what is the equation for all these 4 different types of feedback, you can just solve the KCL and KVL around the loop. I'll be doing it for only one, which is the voltage series feedback, but you'll see that the equation will, in this case, the equation of the feedback will remain same, irrespective of what you are actually doing with the feedback, whether it's voltage series, voltage shunt, current series, or current shunt. You'll have this same equation of the feedback, given that you are representing the A and beta terms correctly. Now for voltage series feedback, you can go through this these set of equations, which is nothing but defining the voltages correctly and then doing the KVL around the loop. So I'll not go through the exact set of equations over here, but you can check the mathematical valid, whether they are mathematically valid or not. And I hope they will be, because this is directly taken from the book. And eventually you'll end up with this equation that your gain with the feedback. So the V0 is your output voltage quantity and Vs was your original input voltage quantity. The gain with the feedback is basically the feed forward gain, which is A, divided by 1 plus beta, which is the feedback quantity, times A. Now, again, as I said, that irrespective of the type of feedback, this equation will hold true. Just that the definition of A, so in this case, A was itself a voltage amplification term. So instead of a voltage amplification, if your input is current, it will become a transimpedance amplification and so on. But the equation itself will remain same. One interesting thing to note here is that if your feed forward gain A is infinite, which is the case for an ideal amplifier, that you have an ideal amplifier with very, very high gain, which means A is infinity. So if you divide your numerator and denominator by A, what would you have on the numerator? You'll have just equal to 1 because you have divided it by A. In the denominator, this first term will go away because 1 upon A is equal to 0 when A is infinity. The second term will be just beta because you are dividing this whole term with A. So as this first term goes away and the second term becomes beta and the numerator becomes 1, your overall gain after the feedback is 1 upon beta. So that's a very interesting thing to note, because assuming that your amplification factor in a feed forward path is very high, you are able to create an amplification which is just dependent on the beta term, and overall amplification after feedback becomes 1 upon beta. And that is important in scenarios where you have a lot of process variation and your gain A can become can fluctuate between two large quantities. For example, let's say you have an amplifier for which the value can be anything between 1 million and 10 million. So that's a very large value, but it's not a fixed value. Now, because your value of the amplifier can, or the amplification factor can change between 1 million and 10 million, your output voltage will also change between 1 million times of input voltage and 10 million times of the input voltage. And that's not a good thing to have, because you don't know how much your amplification or how much your output will be, because your amplification factor will change based on process voltage or temperature variation. So these are called PVT variations. Now, if you had a feedback network, which is a ratio of resistors, for example, and a ratio of resistors are usually invariant to process voltage or temperature change or PVT variations. So if you somehow are able to create a network which is this beta network that is invariant of the process, then through this feedback network, what you can say is that your overall gain becomes just a factor of 1 upon beta. And because beta is invariant with respect to process voltage and temperature, your overall gain becomes a constant and it does not vary with respect to PVT, which will not be the case if you just have the feed forward network. So those are the situations where feedbacks becomes extremely important and indispensable in terms of the overall system level concepts. So this table just says what is your A, beta, and AF factors for voltage series, voltage shunt, current series, and current shunt feedbacks. As I said, that the overall equation will not change. It's just that what you define with A, that changes between voltage series, voltage shunt, current series, and current shunt feedbacks, and so on. You can also find out how does the impedances, the input impedance and the output impedance of the circuit changes as you have different kind of feedback. And again, you can calculate this using this KVL equations that are mentioned here. Just go through the equation. It's just very basic implementation of Kirchhoff's voltage laws. And you'll see that the overall input impedance in this case with the feedback is the original input impedance multiplied with this 1 plus A beta factor. So remember, this 1 plus A beta factor is the amount by which your original gain was reducing. Your input impedance is increasing by the same factor for voltage series feedback. Now, whether your input impedance will increase or decrease depending on the type of feedback, for that, we have this table, which I have presented in the next slide. So you see that for voltage series, your input impedance is increased by the factor of 1 plus A beta, but the output impedance is decreased by the same factor. How do you remember that this will happen? Which impedance will increase and which impedance will decrease? Just think about this, that it's a voltage series feedback. So you're taking some voltage quantity from output and putting it back at the input side. So you can probably try to think about it in this way, that you are in a way trying to reduce the voltage at the output because you're taking away some amount of voltage from the output. So you're trying to reduce the voltage. If you're trying to reduce the voltage over current, which is the output impedance, that will decrease. You are putting some amount of that voltage back at the input side. So at the input side, you are in a way trying to increase the voltage. You'll not directly increase the voltage. So don't think that you are actually reducing the voltage or actually increasing the voltage, but your intention is that you're at the input side, you're trying to increase the voltage a little bit. So that's why the voltage over current, which is the impedance, is increased. For current series feedback, your output is current and you're taking away some amount of current. So your voltage over current will increase because your current is getting reduced. You're taking away some amount of current. And you're putting back some amount of voltage at the input side, which means the voltage over current at the input side is also increasing. So you see both are increasing in this case. So what I'm saying is just a way to remember which impedance is increasing and which impedance is decreasing. This does not actually happen in reality. So this is something just for you to remember in an easier way which impedance increases and which impedance decreases. So let's just take one other example, current shunt. So you're taking away some amount of current from the output. If you're taking away some amount of current from the output, the voltage over current at the output will increase. And you're putting back some amount of current at the input. So the voltage over current at the input side will decrease. Okay. So this is just a way to remember things in an easier way or in a faster way. This is not the actual phenomena that happens. So you're not really reducing the voltage or increasing the voltage or reducing the current or increasing the current in any case. And that will be clear if you solve these KVL equations. So this is what you should actually do if you want to be mathematically rigorous. But if you just want to remember what kind of feedback increases your output impedance or reduces your input impedance, you can just do it using the method that I just told you. So that's the basic theory of feedback. Now, the very important thing to remember here is that, for example, if you have a voltage series feedback, your original gain gets divided by a factor of 1 plus A beta. And with this equation in mind, we'll start discussing the next section of our course, which is basically your amplifiers with feedbacks. So as we go there, you have already this exercise for lecture 3, which was posted. And what it says is basically if you have this amplifier model that you have your VS input connected here, because VS does not have a source resistance in this case, so we are assuming an ideal source, and the input impedance of the amplifier is also infinite, so we are assuming an ideal amplifier with an output impedance equal to 0. So everything is ideal over here. But from the output side, you take this R2 resistance and R1 resistance, take a voltage division of those two, and feed it back at the negative terminal of the amplifier over here. So this is just a representation of an amplifier which has a positive terminal, a negative terminal, and an output terminal. Right? So this will also be called an op-amp, as we will see next, or operational amplifier, with which we can design many different circuits. So what we are doing here is basically we are taking the output, you are putting it through this resistance R2, and then R1. The other terminal of the R1 is grounded, and this terminal which has a voltage of VF, that is directly connected to the negative terminal of your op-amp. So this is what you are doing here in this particular circuit. Now, if you are asked to find out the V0 over Vs, you can do it using nodal analysis that you have already learned in 3111. So for that, what will you do? You'll just represent Vs, which is basically the source voltage, as Vi plus Vf. So the source voltage is actually this voltage plus this voltage drop across R1, right? And that you can write as Vi plus R1 divided by R1 plus R2 times V0 from the theory of your voltage division, that if this point is Vf, and since there is no current going into this part, this op-amp has an infinite input impedance, so there will be no current going into the op-amp. The voltage Vf will just be a division of this R1 and R2 resistances, and that will be multiplied with this V0 voltage. So your Vf is basically R1 divided by R1 plus R2 times V0. Also, you can represent V0 as AV times Vi, because you see that these are the same points. So this terminal is exactly equal to this terminal, which is V0, and this voltage was AV times Vi. So from here, you can represent Vi as V0 over AV. So now we can go back to your first equation. Let's call it equation number 1. And that equation number 1 can be written as Vs equal to Vi plus Vf. Now, Vi can be represented as a function of V0, and you have already represented Vf as a function of V0. So you have V0 times 1 over AV plus R1 divided by R1 plus R2. So from here, you can find out what is your V0 over Vs, and that would be 1 over 1 by AV, 1 divided by AV, plus R1 divided by R1 plus R2. So that's your overall equation for the V0 over Vs. And this is something you do it by nodal analysis for the feedback network. So you see that there was a feedback from the output to the input side, and you just solved it using the nodal analysis. You can also solve it using the equation of feedback. So what was the equation of feedback? And let's call it the A beta approach, the equation for feedback. And using the A beta approach, you can write down the overall gain as A divided by 1 plus A beta, right? Where A is basically the voltage gain in the feed-forward path, and beta is the gain in the feedback path. So what is the gain in the feed-forward path? This is equal to AV, right? That's the gain of your amplifier. What's the gain in the feedback path? Again, it's just the voltage division between R1 and R2. So this is what you have in the feedback path. This is what you have in the feedback path. What is the voltage that you're feeding back? The voltage that is developed across R1. That is the voltage you are feeding back. What is that voltage? That voltage is a ratio or a division of R1 divided by R1 plus R2. So that is equal to your beta. So this term is basically equal to your beta. So if you just write down the formula as A divided by 1 plus A beta, this will be AV divided by 1 plus AV times R1 divided by R1 plus R2. Now look at these two equations. The one equation that you found out using nodal analysis or KCL and KVL versus the equation that you found out using the AV approach. Both of them are exactly the same. Why? Because just multiply the numerator and denominator of this equation. Let's call it equation number 2. And let's call this one as equation number 3. So if you just multiply the numerator and denominator of equation number 2 with AV, you'll get this equation number 3. Because your numerator 1 will be multiplied with AV, you'll get AV. In the denominator, you'll get 1 plus AV times R1 divided by R1 plus R2. So see, in this way, Just by using the formula from your feedback theory, which we just learned, you can find out what will be your overall gain, and the analysis or the time that you take to find out the gain becomes much smaller. All right. So with that, we'll move to the next part where we are going to talk about the details of analyzing feedback-based circuits. So right now, what you have seen is a very simple example and a very simple explanation of how you can do the nodal analysis and you can do the feedback-based analysis and come to the same conclusion or come to the same equation. But many a times you'll see that your equations are or your circuits are much more complex, and then finding it out from the A beta based approach is also not that easy. So in that case, we will be using something called a loop gain based approach, which is a third approach. So we have already seen nodal analysis, which is the first approach. We have seen A beta based analysis, which is the second approach. And third thing we'll learn is called a loop gain based approach. And that is something we are going to see next. And we'll not go into details of that right now. We are going to see all the details in the Friday's lecture. But right now, what I'm going to talk about is basically the fundamentals of an ideal op-amp assumption. So let's say you have the same network that we had seen in the previous PDF, that you have an R2 resistance coming from your V0, and then an R1 resistance that is connecting this point to ground, and this point's voltage is VF. So if you assume that this op-amp is ideal, in that case, you'll have an infinite input impedance, you'll have a zero output impedance, and have an infinite gain. So those are the assumptions for ideal op-amps. Now, again, if you are trying to draw the equivalent circuitry for this op-amp, you can draw it like that. But in this particular example circuit, you can find out what would be your overall gain. If you go back to the previous PDF, you'll see that your overall gain is AV divided by 1 plus AV times R1 divided by R1 plus R2, which you got using two approaches. Now, if you assume your AV to be infinite, and that is the assumption for ideal op-amp case, if your AV is infinite, what would be your overall gain? So you cannot have this AV in the numerator anymore because that is infinite. So you have to divide your numerator and denominator by AV. That actually gives you this equation that you had earlier, the equation number 2. And from here, what you get is 1 divided by this first term will become equal to 0, because 1 upon AV with AV being infinite is equal to 0. So what you'll be left with is R1 divided by R1 plus R2. Now, of course, this entire R1 divided by R1 plus R2, that's in the denominator. So you can take the R1 plus R2 back in the numerator side. So let's call it R1 plus R2, which means that in the numerator, you'll have R1 plus R2. In the denominator, you'll have R1, which means you can represent this as 1 plus R2 over R1. And this is called a non-inverting amplifier configuration, where the gain is 1 plus R2 over R1. So as you see that you have this op-amp where you're providing the input to the positive terminal, and you're taking the output from the third terminal here, while the negative terminal is connected to the feedback. So this is called a non-inverting op-amp configuration, because you see that the output or the gain is a positive quantity. It's not inverting the input phase, and the value of the gain is 1 plus R2 over R1. So we see that we are writing the same formula over here, 1 plus R2 over R1, and that's for an infinite feed-forward gain. When you have an infinite feed-forward gain coming from the amplifier, you have this as, you represent this as A infinity. So we'll stop here and we'll resume in the next lecture, and we'll look into the loop gain-based approach.